Hello everyone, it's a great honor to have the opportunity to report here today. The title of my paper is an OO-based approach of computing, offloading, and resource allocation for large-scale mobile edge computing systems. My speech will be divided into 5 parts. The first part is introduction. Mobile edge computing (MEC) is an innovative paradigm designed to offer rich computing resource for mobile device. MEC can achieve less latency as well as little workload, and offer an improved user experience compared to mobile cloud computing. Existing studies on MEC just focus on optimizing the execution latency or energy consumption of mobile devices, while neglecting the energy consumption of the edge servers and densely deployed small cells in 5G era. So we studied the large-scale MEC system offloading problem, which is NP hard. Then the original problem is divided into 2 sub-problems, and we obtain the closed-form solution of the optimal resource allocation and an arbitrary given task placement policy. Finally, we introduce the theory of ordinary optimization, intending to get a near optimal task placement policy. The second part is system model and problem formulation. Figure 1 is a model of the large-scale MEC systems. We assume that there exists n wireless base station, and each base station is equipped with an edge server. There are m mobile users, and each user have a computing task which can be computed locally or offloaded to edge server. Then we can get the transmission latency and the transmission energy consumption when mobile user offloads the task to base station Bj as equation 2 and equation 3. We can also get the local latency and local computation energy consumption of task as equation 4 and equation 5. Similarly, we can get the edge latency of task as equation 6. As we can see, the edge latency of task consists of computing latency and transmission latency. As for energy consumption, we use a utilization-based model to represent edge server power consumption. It can be seen from the equation 7 that PGE consists of 2 parts. The former is the extra power consumed when processing tasks, which is related to the workload of the server Bj, while the latter is the power consumed regardless of whether the server is working, which is irrelevant to the workload of the server. That, for the sake of convenience, we only consider the former. Therefore, the extra power of edge server Bj consumed by task can be expressed as equation 8. Consequently, the edge consumption of task Ti processed on the edge server Bj can be expressed as equation 9. Therefore, we can formulation the problem as equation 8. as equation 10 of Worksharing. Equation 10 is a mixed integer non-linear programming problem which is NP hard. The third part is efficient offloading algorithm based on ordinary optimization. We solve the above NP hard problem by dividing the original problem into two sub-problems as follows. Computation resource allocation problem. This problem aims to decide how much computation resource an edge server allocated to each task offload to the edge server. Task placement problem. This problem aims to decide whether each task will be processed locally or remotely, and if offloaded to edge server, it will be overloaded. Let's solve the former problem first. We can see that the resource allocation of one server does not affect the resource allocation of another server when the task placement policy is given. In this case, the original problem will be transformed into a simple impulse N7 convex optimization problems, and JS of which is as equation 14, and the closed form of optimal solution can be found. Then let's solve the latter problem. As we have seen before, we can get the optimal computing resource allocation when task policy is given. So the original problem is simplified to get the optimal task placement problem. Unfortunately, the design space of the task placement problem is extremely large, so we consider introduce a conception of ordinary problem optimization to solve this problem. Ordinary optimization was first proposed by Huang et al. Soft optimization for hard problems is the quintessence of OO, which means after solving the goal, the hard problem can be tackled within a tolerable time. It is highly impracticable to find the global optimal solution, so we seek to find the nearly optimal solution instead with a high probability. The objective can be formed as equation 17. Here, G denotes the good enough set, S denotes the set of a selected solution, PR, called element probability, denotes the probability that the number of good enough solutions in S is no less than K. O can pick out S to ensure equation 17 holds, and the G, K, and alpha specified by user. Combining with the theory of OO and theorem 1, we designed the OO-based algorithm. Well, 1 aims to replace theta with theta n when n is equal or greater than 1000. We can treat theta n as a reasonable representative of theta. Lines 2 to 3 estimate the performance of each sample in theta unraveling. Lines 4 to 6 aims to find the set as lines 7 and 8 evaluate the performance of each sample in as ambitiously. Finally, the sample with the best performance of the good enough offloading policy is found. The fourth part is performance evaluation. We compiled the proposed algorithm with three baseline algorithms at different beta 1 and beta 2 values to verify the effectiveness of algorithm. In Figure 3, we compiled the performance of the aforementioned policies when beta 1 is 0.9 and beta 2 is 0.1. In this case, we are more concerned about the average latency rather than the average extra edge server consumption. Figure 4 illustrates the performance of four offloading policies when beta 1 is 0.1 and beta 2 is 0.9. Contrary to the above situation, in this case, we are more concerned about the extra energy consumption than task latency. Figure 5 illustrates the performance of four offloading policies when beta 1 and beta 2 are 0.5. In this case, we consider offloading task and extra offloading task latency and extra energy consumption equally important. We can see that our proposed algorithm is significantly better than the baseline algorithms in all three cases. The last part is conclusion. When we first studied the problem of minimization the latency and server energy consumption in large-scale MEC systems and illustrated this problem is NP hard. To solve this problem, we consider dividing the original problem into two sub-problems and design an efficient offloading algorithm based on ordinary optimization. Finally, simulation results have shown that the OO-based offloading policy is more efficient than other three baseline offloading policies. Thank you for listening.